the next one, x cubed minus x. All right, let's go find it. Oh, good, we can see it. So, if I fold it down this line, does it fold on top of itself? No. But if I rotate it 180 degrees, look what happens. It falls right back on top of itself. So this is a no, yes. So if I say yes about symmetry about the origin, then it is odd. Okay, let's do the next one. All right. So this one, if I fold it down this line, no. If I rotate it about this line, about this point, no. So this is a no again. No, no, neither. All right. This one, if I fold it down this line, yes. Okay, so this is a yes, no, even. If it is symmetric about the y-axis, even. All right, let's go find this one, L of x. That's not it. There's one. Okay, fold it down that line.
Yep.
Yes. So here we go, yes. So if it's yes to the y-axis, it is even. All right, let's go find M and N. We'll look at both of them. Here, oh, they're both right here. No, no, this is a no-no. So it's neither. And this is just the reflection of this. So it's a no-no.
What if it's both?
It can't be. It can't be symmetric to the y-axis and the origin. That's a good question, though. So both of these are no-nos. So, like I said on Friday, most graphs are neither even nor odd. Most. We have to work real hard to come up with one that is even or odd. Okay, and that's what number 2 says, why don't we talk about functions that have symmetry to the x-axis? And I drew one of those on the board, like this one, a sideways v. That's symmetric to the x-axis, right? But is it a function? No, they are not functions.
What are they called?
Okay, they fail the vertical line test. Okay, so that's why we don't talk about functions that have symmetry to the x-axis, because it can't be functions if it's symmetric to the x-axis. Okay, so number 3 was doing the same thing, determining whether a function is even or odd or neither, but determining that algebraically. So we have 2 tests for that. Well, both tests start off the same way, but the result gives us 2 different things. If we plug in the opposite of x and we get out the original function, it is even. If we plug in the opposite of x and we get the opposite of every term in the function, the opposite of the entire function, it is odd. But if we get a mixture, some terms stay the same, some terms switch to the opposite, then it is neither. Yes, ma'am?
How do you know which one to use?
Well, every time you do the same thing, and then you just look at your answer to decide which one it is. So every time we plug in negative x. Okay? So on this one, I plug in negative x. All right, the other important thing here to be able to do these is we have to remember that a negative raised to an even power is positive, and a negative raised to an odd power is negative. Okay? So here we have a negative to an even power, so it becomes positive. Here we have 2 times negative x, so we get this. All right, so we plugged in negative x, and here's the test every time. After you plug in negative x, then you compare. The first term stayed the same, the second one changed. I got a little bit of both, neither. Okay? So let's do h of x. I'm going to switch colors here. So we plug in negative x. Negative to an odd is negative. And a minus a negative is positive. All right, now we compare. The first one changed to the opposite. The second term changed to the opposite, which means it's the opposite of the entire function, odd. Okay, next one. Same process every time, plug in negative x. Okay, so a negative to an odd is negative. But there was a negative out in front, so it becomes positive. A negative to an even is positive. And 3 times a negative is negative. All right, so this is the point where we compare what we have now with what we started with. So the first one changed to the opposite. The second one stayed the same. I can stop comparing. Neither. It either has to all be the same for even or all be opposite for odd. Anytime we have a mixture, it is neither. Okay, last one. Same process. Plug in negative x. Okay, so when we plug in negative x, a negative to an even is positive. A negative to an even is positive. Same, same, same. Even. Alright, so questions about that? Okay, so there's 2 ways I could assess you on this. On our next quiz, I could ask you to describe it graphically, and that's where you're looking, symmetric to the y-axis, or rotational symmetry about the origin. Symmetric to the y-axis, even, rotational symmetry about the origin, odd, or most of them will be neither. Okay? But if I ask you to do it algebraically, I have got to see where you plugged in negative x. That's where your points will come from. When I assign points to my grading rubric, that's where the points go. Did they actually plug it in algebraically? Because I know you can punch all these in on your calculator, but there's a dual part to the standard, and one of them is graphically, and the second part is algebraically. So make sure you can do it algebraically, because this is not hard. If you understand this, these are pretty easy. Okay, and we'll do some more in preparation for that next assessment. All right, let's take a look at number 4. So number 4 was end behavior without a graph, and this was review. So when we look at end behavior without a graph, we're looking at 2 things. We're looking at the degree of the function. Whoops. The degree of the function and the sign of the leading coefficient. Now the leading coefficient is when it's in standard form. So if it's not in standard form, you have to go hunting for the one that has the biggest exponent. So let's take a look. And this is how we set it up. So we have an even degree function or an odd degree function. If it's even and that leading coefficient is positive, then as x approaches positive or negative infinity, y approaches positive infinity. Either way, it's going up, 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 up. If it's even and negative, as x approaches positive or negative infinity, both ends, y approaches negative infinity, both ends fall. Okay, so this was reviewed from part 1 of unit 1. Now, if the degree is odd and the leading coefficient is positive, then as x approaches negative infinity, so does y. And as x approaches positive infinity, so does y. Because this falls to the left and it rises to the right. This is the opposite of that. It rises to the right and it falls to the left when we have an odd and a negative. So as x approaches negative infinity, this one's going up on the left side. Y approaches positive infinity. And as x approaches positive infinity, it goes down on the right. Y approaches negative infinity. Okay, so that's what we're looking at. This term right here. This term tells me all about the end behavior. So it's odd and negative. So as x approaches negative infinity, y approaches positive infinity. And this one, as x approaches positive infinity, y approaches negative infinity. Because it's odd and it has a negative leading coefficient.
But does the 3 or the 5 determine whether or not it's like odd or even?
The degree of the function is determined by the power. So the 5 determines that it's odd, and the negative 3 is the negative leading coefficient. Okay?
And you ignore the powers of the other two coefficients?
You do, because the degree of the function when it's written as a sum like this is the term with the highest degree. So this is also written as a sum and difference, so we're only looking at this one. So the power is even, so it's an even degree, and the leading coefficient is positive. So on this one it's going to rise, and I'm going to take a shortcut here and just say as x approaches positive or negative infinity, y approaches positive infinity. And this one is even also, but it has a negative leading coefficient. So this one, on both ends, whether x approaches positive or negative infinity, the y's are falling, so they are approaching negative infinity. Okay, now number 5, you have this salmon colored sheet to stare at. Okay, so on this one, you were just writing things down. What is the degree? 2. What are my x-intercepts? I can read them straight off of here. Negative 2, 0, and 0, 0. So this one had 2 zeros. The x-intercepts are also where the zeros of the function are.
Why do you write plus or minus? Do you just instead of writing twice?
Yeah. Alright, this one has a degree of 2. My x-intercepts are 0, 0, and 1/2 0, or 0.5. We had 2. Okay, this one has 3, negative 1, 0, 0, 0, and positive 1, 0. And once again, we could read these straight off the graph. This one has 3 also. It is at negative 1, 0, 0, 0, and then 3, 0. Okay, this one has 4. The degree is 4. And they are negative 2, 0, negative 1, 0, 1, 0, and 2, 0. And this is the same. They're all the same. Okay, so hopefully you noticed something with the degree of the function and the number of zeros. And we talked about that in the second part of Unit 1, that when we count up the number of zeros, it'll be equivalent to the degree of the function if we take into effect the multiplicity at the root. So if it bounces, it would count as a double. So we would count it twice, right? So if we're not counting the multiplicity, we're going to notice that the number of zeros is at most the same as the degree of the function. Okay? All right. Today we're not adding much to it, but you're going to need your calculators for what we're doing.
You're a little too cold.
Okay, I'm going to stretch this out. And I'm going to see if my graphing calculator will open up. And we'll talk about these things. All right, now, do you guys remember domain and range from Algebra 1? Domain is all the possible input values for a function. Range is all the possible output. So domain has to do with your x. Range has to do with your y. Okay, so it is working. Fabulous. All right, the next thing on here are max and min. All right, I want you guys to add this above max and min. These are called extrema. So whenever you see directions that say give all absolute, local, relative extrema, state the extrema. And that's what it's talking about, max and mins of the function. So when we look at a function and it has hills and valleys, the peak of the hills, the top, those are maxes. The bottom of the valleys, the min. And then intervals where the function increases and decreases. So we're going to talk about all these things today. All right, let's look at the first one. Now please notice, same exact functions. You have it here, but this is not enough today. We're going to need the calculator to figure out other parts of these. Okay, so when we look at this first one though, we can see that this function from our pink sheet, salmon colored sheet, looks like this. It's a parabola. It goes forever left and forever right. There are no excluded values for x. So the domain would go from negative infinity to positive infinity. Every x value is a possibility in this function. Nothing is excluded. Okay, now we can also tell that we have this bottom point right here. And on a parabola, what do we call that bottom point? It is a minimum, and this minimum is the vertex. So this one has no max. There's no hill. There's no top of a hill. There's just the bottom of this valley. And that is our minimum. So now we need to learn how to find the min, or remind ourselves how to find the min using a graphing calculator. So if you guys could take those out, and we're going to enter that function into y1. So the function is x squared plus 2x. X squared plus 2x. Alright, now this is where I wish actually that we could just use Desmos, because Desmos is so nice. All I'd have to do on Desmos is click right there, and it would pull it up for me. And I wouldn't have to do anything else. The problem with Desmos is you have to be online, and if you're online, then we can't use it as an assessment tool. So here we go. I'll teach you how to use the calculator for this. Okay, so to find this point on the calculator, we know it's the bottom point, we know it's a minimum. So anytime we want to calculate a point on a graph, we would go second button, and trace is calculate. And here you're going to find anything we would need to know. You can actually find zeros. You can find minimum values, and you can find maximum values. Okay, so in this case, this is a min, so I'm going to choose 3. Now, your calculator starts, like mine always starts on the y-axis, and do you see it's prompting you? This calculator is prompting you to do a left boundary. So to go to the left side of this min. So to go right or left, we use the right and left arrow keys. I need to go to the left side of this one. So I'm going to take the cursor and move it so I can tell it's on the left side of that lowest point. Yes, sir?
Negative 9.
Okay, so when we're on the left side, we're going to hit enter. Okay, and your calculator will give you this vertical line for the left boundary. Now do you see what it's prompting you for? It says, okay, now set up the right side. So we're going to go to the right side of that lowest point. And when I can clearly tell I'm on the right side, I'll hit enter again. So now that minimum value is in between these two boundaries, and a check step for you guys, these arrows should always be facing each other. Now we always just hit enter for guess. And do you see the calculator gives us this minimum? -1, -1. This minimum value occurs at the point -1, -1. So this point right here is -1, -1. Now, the min value is y equals -1, and it occurs where x is -1. So you could write it like that, because minimum talks about the lowest value of the function. These two are actually talking about those y values. So we have a minimum value of -1 at the point x equals -1. All right, so now that we know this minimum, we know that's the lowest y value on the graph. So range goes from least to greatest for our y's. So we know what the least y value is. It is -1. And it actually includes that point, and that is why I have the bracket. So it goes from -1 to positive infinity. Now, the next thing that we're going to talk about is intervals where the function is increasing and intervals where the function is decreasing. So we are going to write it as an interval, and we always use x values to do this. So we start on the left side, always start on the left. Now, if I'm following along this function, starting on the left side, do you see I have to go down until I get to this min? If I'm going from left to right, we always go left to right, I have to go down. So that means I start off at -infinity and I go down, which is a decreasing interval, until I get to an x value of -1. So that was going down. Well, what happens when I get right here? Now I go up. From this point on, the function is increasing. It's going up. So it increases from that -1 to positive infinity. Okay. Sometimes I have my students, and you guys are welcome to do this, if you have a graph for increasing, decreasing, you could just put a little X number line down here, and you can put the value here. The X value is -1, so a number line goes from -infinity to positive infinity. So you could ask yourself, what am I doing as I go left to right? I'm decreasing from here to here. And then what am I doing after that? I am increasing from here to here. So this way on the number line, you can see we have that decreasing interval from -infinity to -1. And then we have an increasing interval that starts at -1 and goes to infinity. So if you want to, you could always put a little number line up under your graph and mark your x values for your extreme on there, and that always helps you figure out what your intervals of increase and decrease are. Okay, so let's go back and let's take a look at our next one. So if we look at this next graph, we want to go ahead and graph that, and it's -2x squared, and make sure you use the negative sign when you mean negative. Oops, I forgot to clear all my stuff out. Start over. -2 delayed. I know, you guys are done and waiting on me. Negative 2x squared, and then plus x. Okay, so if you look at this graph, it's going to look like this. All right, and we want to find this maximum value. So to find the max, this time it's the highest point. It is a max. So to find that, we do second trace, and this time choice 4. But then the rest of the process is exactly the same. We go to the left side of the max, and we set up the left boundary. And then we arrow over to the right side of the max, and we set up a right boundary. Now, do you see how mine is not perfectly symmetric? That's okay. It doesn't matter. And then we hit enter for guess. And this is what we get. All right. So, what does this round to, guys? 0.25, yeah. So this right here would be the point, 0.25, 0.125. That's what that point is. Yes, ma'am.
Why wouldn't we round the second one up to 13?
You could. I didn't because this one had a whole bunch of numbers following it. And these were 3 9s in a row, so it would be like 0.250. Okay, so we'll come back to that graph in just a second, but now we know what that point is. We know this one looks like this, and we know that this point right here is 0.25 and then 0.125. Okay, now, because it goes forever left and forever right, even though it's going down, the domain of the function is negative infinity to positive infinity. Now, this time we have no min. This is a max. So the max occurs at this point, so my y value is 0.125 when my x value is 0.25.
Why is it a negative positive?
Because, well, the domain of every polynomial function is. Because there's no excluded x values on the domain. Any x value I plug in is defined. And we do have some functions where there are values for x that if we plugged them in, we would get something that was undefined. And those functions do have restricted domains. This one doesn't. It keeps going forever left and forever right. Even though it's going down, it still keeps going forever left and forever right. Now the range is least to greatest. This one's going down forever. What concept means down forever in mathematics?
Infinity.
Negative infinity. Okay? Up forever would be positive infinity. Down forever would be negative infinity. So with our range, we always go least to greatest. Well, if I start down here at the bottom, it's pointing down forever. So my least value is negative infinity. To my greatest, what is the y value right here? What is the biggest y value this function can have? 0.125. All right, intervals where the function is increasing and decreasing. I'm going to go back to my graph real quick. I'm going to draw that extra number x-axis right here. And I only have one little max here. And the x value right there is 0.25. Okay, so it goes from negative infinity to 0.25, from 0.25 to infinity. All right, I always start on the left. To follow this function, what am I doing right here? Am I going up or down? To go left to right, I'm going up. So this interval is increasing. It is increasing from negative infinity to 0.25. Okay, as I continue to travel along the function, what am I doing on this side of the function? I'm going down. This is a decreasing interval. So it decreases from this x value of 0.25 all the way to infinity. Okay, so let's go and fill those in. So it was increasing from negative infinity to 0.25, and then it was decreasing from 0.25 to positive infinity. It's hard to see. 0.25. Okay, so but both of these were just quadratics, and they only had either a max or a min. But if we look at the next one, it has both. Okay, so this one looks like this. We can see it on our sheet. It has a max right here and a min right here. Now, this max and min are a little bit different than these. This minimum value is actually called an absolute min, because it is absolutely the lowest point on the graph. So this is an absolute min. This point right here is considered an absolute max. Now, even though this is a max, it is not the highest point on the graph. And even though this is a min, it is not the lowest point on the graph. It's lower than the points around it, and this one's higher than the points around it. That's what makes them max and min, but they're not the absolute. So do you guys remember, actually you may not have studied this. They're called relative or local.
I remember this.
Okay, good. So either way, relative or local means the same thing. So if I ask you on an assessment, are there any local max or mins, you should know what that means versus absolute. Now, what you're going to notice is over time we quit designating which one's which. We just call them all max and mins. So this one goes forever left and forever right. And you're also going to notice, because we already know this about end behavior of odd functions, it's always opposite. One end goes up, the other end goes down, forever. So anytime we get an odd one, the domain and range are negative infinity to positive infinity. Okay, I would like you to use your calculator and see if you can find these two values. You've got one max right here, one min right here. one it is. It's just opposite signs. Now down here, you're gonna notice we have a lot of different ones. They're not always just opposites. This one's opposites because the function's odd. Because the function's odd, it has to be. Because if we rotate it 180, it falls on top of itself. So, all right, now, hold on. So we've got this point right here, and this point is negative 0.577, and then 0.3485. 85, not 4. And then this point right here, which would be our min, is positive 0.577 and negative 0.385, and that only is true because this function has odd symmetry. It's an odd function. Alright, so when I do that increasing, decreasing this time I have two things I have to look at. I have to look at this max, and this max happens when x is negative 0.577, and then I have to look at this min, and this min happens when x is positive 0.577. So if we look, it goes up here, so it's increasing. It goes down here, it's decreasing. It goes up there, increasing. So we have two increasing intervals. We have one from negative infinity to negative 0.577. And then we have a second one. So it's not just one, there's two. So we have a second one from positive 0.577 to infinity. Now there's one little interval over which the function goes down, and that's from an x value of negative 0.577 to positive 0.577. Okay, so as we travel left to right, this one goes up here and up here. Left to right, we have to go up and up. And in this interval, it goes down. Positive, negative, positive.
So for increasing, wouldn't the second one be the other decimal?
You always use your x values for increasing, decreasing. So you're describing how y is changing over what x interval. So increasing, decreasing is always your x values. Okay, so let's all take a look at the back of this now. The back of this worksheet is your homework. Okay, so one, you were given the graph, but you're going to need to use your calculator. And so we're doing domain range, max and min, local versus absolute today. Then we'll kind of lump them all together pretty soon. And then increasing, decreasing. And you have one where you're given the graph, and then three where you totally have to use your graph calculator. Any questions about expectations? Okay, hopefully tomorrow we will go back to video lessons, so you guys can definitely ask more questions during class.